Hello. All right, I get the flashing red light and the numbers tick in. We're live. Hello, everyone. I'm Verdi Augusto. This is the Schumann Resonance Harmonics channel on YouTube and Facebook, more or less. All right, thank you for being here. I have the gain on the mic turned up way high because it's like 1 in the morning. It's the 19th of May. And there's people upstairs sleeping, so I'm going to try and whisper. Um, all right, so my guides suggested that I do this video, just because I needed to do a video with the observation of what's going on at Tomsk, but also because I looked at it, and let me just say this. At first, my initial response to these things is, the spike is in the middle of the day, it's normally because of the ionosphere. All right. So I looked at this one and it's okay. All right. So our time is the local weekend. All right. Even in the small things, for what is a small thing for me, it might be a good, solid, significant reminder for other people. So even in the details and crumbs of stuff, it can be a good review for people of what's what, of an orientation. Okay, so I have to remember that even if it's simple for me, it may be a basic that needs to be gone over with the people, with the 10 of you. Okay, so once again, the white numbers here are the local time at Tomsk, and it's like Tomsk summer savings, daylight saving times or whatever. But that's our Tomsk standard time. All right. So, and this is in the 24-hour setting. All right. So the yellow numbers underneath are the UTC, and the UTC starts out in Greenwich, England. It used to be Greenwich Mean Time because it was based in Greenwich. It's the same type of thing. Every time zone is an hour, but it's now UTC, Universal Time Coordinated. So, and if you see over here, it also tells you that yellow is the UTC. All right, that's how I know. All right, so what we're looking at here is 10 o'clock in the morning. All right, so 0 is midnight. Okay, so, all right, on the 18th, this was yesterday, okay, or it was almost like 2 days ago over there, whatever. All right, so this is the middle of the night. Again, when I look at these things, my first thing is, this, the atmosphere is, it's tightened up, but this is when it should be sleeping. This is a significant peak because it's the middle of the night. Not because of the number, but it's the middle of the night. To where usually this point here is where it's dead quiet, and there's a big spike there. So that, let me, first off, let me just show you the weather at Tomsk. Okay, it was sunny during the day, and in the afternoon, it was 55, 0% humidity. Evening, it's clear. Overnight, it's cloudy. So there is some clouds over there. I'm not sure how the cloudy affects the Schumann resonance. I think having a cloud does kind of help keep it intact, but I don't have any studies on cloud formation and cloud cover and the Schumann resonances, just for the record. All right, I haven't come across any. All right. So I'm not sure how they factor that in. All right, but theoretically, the cloud is water vapor. It's not an electron barrier. All right, from what I just generally gather, I am understanding. All right, all right. So all right. So somewhat cloudy in the. All right, so that we're factoring that in there somehow. I don't know, but it's the middle of the night here. All right, and so 0 is midnight. 1, 2, 3, 4, 4 in the morning. This is usually when there's like nothing there. This is a what the hell? It's the phrase I use. A synchronistic mode. All right, so the synchronized, like synchronized swimmers. All right, so there's the peak at the waveform. Okay, so remember, it's important to remember when the modes, when they're figuring out the coloring scheme, they're figuring out what the modes are. It's based on the size and the shape of a mathematical formula. So they mathematically figure out the size and the shape of the mode 1 versus mode 2, 3, or 4. All right. So they've broken the wave up like a spectrum analyzer. If you've ever seen that with an equalizer, there's band. It's a bandwidth. So they break up the frequency in different bandwidths. It's hard to explain this. Based on the size, the height. Again, amplitude is the height of the signal. So there is a theoretical shape of each one of these modes that fit together. So when these all kind of look like nested dolls, I call it nested dolls, this is high amplitude. This is not coming from the lower atmosphere where the amplitude and quality are more closely matched. We're looking at two things. This is part of the puzzle when I look at this, as I'm comparing how all of the amplitude signals were together as a group. They're all synchronized in this case. Okay, so that's one of the factors, one of the axes that I look at when I'm figuring out how to figure this out. Okay, so this is all of them synchronized together. That's how you're getting the rust color always, almost like always around this. You're getting the rust color because it's the size and the shape of the wave that's coming in. And this is the vertical. All right, this is the vertical wave coming in that way. All right, and so then the next thing is you have to compare the mode 1 and mode 2 together, mode 3 together. So the amplitude and quality of mode 1 together. I'm looking at that as a signal. So the white here and the white here. All right. So what's happening with the two of them together as a group, as opposed to all of the amplitude? Boom, like that. This right here is all of the amplitude, all of the height of it, the wave coming at you like that. Okay, nested together. This one here, the quality, that is the magnetics of the electromagnetics portion of that. So when we're looking at this, it is, again, the white mode. When I say white mode, it's quality 1 and amplitude 1 and frequency 1. White mode, it covers, all of those together. Essentially, when I say white mode, as opposed to amplitude 1 or amplitude mode 1 or quality mode 1. White mode is all of them together, and you look at the white on here. This is all made from the white of white mode, the electromagnetics together. The frequency is, again, you got to remember, it's the wave, the peak, and these are like 8,000 kilometers, 8.12 thousand kilometers. These ones here, and these are fairly big waves. The 26 number here, that's a large number relative to frequency. The 25 there, a lot of these times these go together. The quality, these two numbers match up or are very close. So if there's a high number here, like 26, will a lot of times be a high number here, like 25. But you see down here, this is a very low activity here for the green. This is the magnetics, all right? 9, that's not much. However, 9 is here on this chart. You know what I mean? It's all relative. You look at that. So the peak here of 25, that's there, and 25 is double the 10.5 of the right? Double the magnetic of that. So this is obviously a bigger magnetic signature. This is what you have to look at as well. The Schumann resonances are the magnetics. They're coming from the magnetics of this, and the magnetics are horizontal. So This right here is a significant number for considering the time that it's supposed to be, we're supposed to be sleeping. There's a loose ionosphere, so this, the Schumann resonances are first and foremost caused by lightning discharge. Okay. I have shown you a picture, right? This is our ionosphere here. All right. So this is our ionosphere here, okay? This is the electron density and cubic centimeters, okay? So there is this bulge of it that's primarily there most of the time, the F layer, okay? So during the nighttime, when the sun's radiance is not activating the ionosphere, there shouldn't be much going on. So that is a significant burst of lightning that's showing up in the middle of the night. You got to remember, this is the lightning is the primary cause of the Schumann resonances. And I wanted to show you something else too. All right, so this is the real-time auroral activity. Okay. So this is giving you the wind speed, the wind density. Okay. This right here is the magnetic side of this is NANO-Tesla. This is measuring the Earth's magnetic field link, all right? This is NANO-Tesla. That's 1,000 times more powerful than the Schumann resonances. You have to remember this. The Schumann resonances are measured in the pico-Tesla range. Not the nano-Tesla. Earth's magnetic field itself, the lower DC circuit is nano-Tesla. The upper DC circuit is nano-Tesla. So the interplanetary magnetic field, that's nano-Tesla, showing you right here. And in the direction is north. Okay, so north is generally above us, relatively speaking. Relative to the map, how they have it, so I guess that's the best way to think of it, So I don't have a good way of explaining this to you, but I wanted to show you, like, this is where it's at, 8.89. They give you the height of it is 10. I'm not sure if that changes, but that's a pretty tall signal there, 8.89. All right, so 10 or greater would be moderately strong. So it's calm. It's relatively calm. All right. Okay. 8.89 is relatively calm. I know these numbers here, that's fairly calm, and that's fairly calm, let's just say. So less than 400 would be normal speed. Okay, yeah, the density, what did I show you? Less than 10 is low density. This is 4. Yeah, so this low activity, generally speaking, from the sun. Okay, we're not getting bursts, but it's in the nano-Tesla, and so you have to remember that as well. Like, this is really important. I gave a description of, let me see if I can find this. Oh, please. Okay, I found it. All right. So, Professor Schumann, all right, so here we are. Schumann resonances are caused primarily by lightning discharges. All right, so just really quick, this was a post that I made to the Facebook, the Facebook group that goes with this, the Schumann resonance harmonics. This is something that I had put up, the announcement, the most recent announcement that I had pinned to the top. And so I put it this way: Earth keeps her heartbeat on her chest. Telluric currents are not the Schumann resonances. Okay, so there's been from the beginning, people confuse the telluric currents with the Schumann resonances. Folks as well confuse the Earth's natural currents, which are the Earth's currents. The Birkeland currents also are considered part of the telluric currents, but the Birkelands are a little different than the telluric currents of the Earth itself. Okay, these are all different kind of circuits that work together, but they also have a different purpose. Like your body has a capillary system and different ways it moves energies around your body. It's the same thing with the Earth. That there's certain circuits of high voltage and a lower voltage. That's important to remember. Like your phone, if you plug it into the wall, there's 120 volts there, but the phone itself only operates on 5 volts. You have a little adapter with a little plug, right? The wall current is 120 volts, and your phone is 5 volts. Okay, it's the same type of thing. The upper ionosphere is sort of like a jello consistency. It's a plasma that's got a type of density to it. But if you could easily punch through it, it's like a soup. It's a heavy gas. It is a gaseous form. It moves. It's very fluid, but it's a thicker type of gas. It doesn't, like Jello is a good analogy for it. It's kind of see-through, but it's got a certain density. It's very kind of sort of lightweight, but it sort of holds together. So you can get that impression that there's not much to it, but it's like a big electrostatic jello. It holds itself in charge. It holds itself in place because of an electric charge. All right. So Schumann resonances are caused primarily by lightning discharges, which radiate out into the atmosphere, converting amplitude into quality, which is the cohesive wave of magnetic flux bouncing between the ionosphere and the Earth's surface. These are subtle energies of pico-electron volts and pico-Teslas. Earth's natural electromagnetic field is measured in NANO-Teslas, which are 1,000 times stronger than the Schumann resonances. Okay, so that's what that little n there stands for, nano-Tesla. Okay, and larger than, they're giving the numbers here, larger than 10, moderately strong, larger than 20. All right. Okay, all right. All right, so it's best to think of Schumann resonances as the breathing function and not Earth's heartbeat function, if a biological assignment to function is necessary. Earth's internal circuit is considered the lower DC circuit. Earth moves her power internally as a current, which is a direction. Her power does not leach out into the atmosphere as people seem to think it does. Like it's exuding, you have an energetic field, but that's different than your etheric energy field is different than the strength of the electrical field that of your heart itself. We're talking about the heartbeat function of you. The electrical signal of the heart is itself stronger than the energetic field that you have. Your etheric bodies do have a magnetic, people have a magnetic personality. That's exactly what that is. I'm one of those people. I have a magnetic personality, very magnetic personality. And so I can affect people at a distance, and that is why your etheric field. But this is where we start getting into the quantum realm of things, where it's thought energy, which is much more subtle, but it's a more directed kind of thing, because it's going to, it's entrained. So the power of the field itself is not as strong, that etheric field is not as strong externally to the heart as the power of the organ itself. This is the heart we're talking about. So we extend this analogy over to the Earth's heartbeat function, that the telluric currents within the Earth itself are much stronger than the etheric breathing energy, as I call the Schumann resonances. It's the breathing energy, the respiration of the planet. A much more subtle energy, like the sigh of the planet, much more subtle than the internal energy going through the planet itself. So again, 1,000 times stronger. So whether we're talking about the intermagnetic field or the Earth's internal telluric heartbeat, her heartbeat, the current that through the ley lines and all of that, that is in the NANO-Tesla. It's 1,000 times stronger than the Schumann resonances. All right, so Professor Schumann had described it as the ringing of the bell. We use the analogy, the ringing of the bell. This is the illustration how Schumann himself had offered it to his class. All right, so let me explain this a little bit of what parts are what. In the bell, the actual bell is hung from a yoke, right, suspended from a yoke, which is firmly attached in the bell tower. Right? The bell swings freely from the yoke. A clapper is attached in the middle of the bell, and it hits the sides of the bell. Right? They move the bell, right? So, as generally speaking, the clapper stays. Right? The clapper kind of stays where it is, and they hit the bell into the clapper, but then at a certain point, the clapper starts moving. All right. The vibration, it hits the bell vibrates. The vibration essentially fills the middle of the bell. All right, and so then a resonant harmonic tone is developed. All right, so in the analogy here, the ringing of the bell, how are we applying this? The yoke, which is stable, attached to the bell tower, you might see it as the planet, which is not going anywhere. There is a little bit of movement there, but it's not going anywhere. All right, otherwise it's all things going. The clapper, the little hammer in there, is a strike of amplitude. Bang! Strike, like when that's what you look at these spikes. Where are we? These spikes here. All right. So when we're looking at this, our first primary thought is this is lightning, not solar radiance, because that's 1,000. It's a different circle, a different circuit, and it's important to remember that. Boom. Back there we go. It's important to remember that the strength of the Earth's ionosphere, magnetosphere, ionosphere, that holds intact as a unit. You have to remember that. Once it hits the natural resistance, the resistance of, I'm trying to think of what the electrical word they use for this is, but it's the basic resistance of the lower DC circuit. That's the first thing that kind of happens. The atmosphere, the differential, the potential, difference of potential between the current and the charge. So when it's set up, the magnetosphere, the ionosphere all acts as one type of circuit, and it surrounds the Earth. Ba-bam! Okay, and holds it intact, like there's a globe. Essentially, that's part of one of the ways it holds it intact. So as the Earth is spinning, it's sort of adjusting to it with the strength of the IMF, the magnetic field. Again, NANO-Teslas. All right. So within the bell, and you have to, the better analogy for this bell analogy would be if you took the bell in half, cut it in half, and on one side of it you have brass, and on the other side of the bell you have the jello substance that would be fairly equivalent to the situation. Now you have one side, like it's a sphere, like, we're doing the best we can with, what we have to work with. So if you can picture the shape, the exact shape of a bell, there's a roundness to it, there's a sphericalness to it. If you took the bell and made it, solid and turned it into an earth, and then you made another bell around that out of the jello, that's close to what we're talking about. The earth itself isn't quite ringing, it's solid. It does ring a little bit, yes it does, but relative to the jello in the earth, okay, our bell that's full of dirt, that doesn't move as much as the jello substance that's out there, the ionosphere. So the ringing comes from the waves in the middle between the hollow bell, Yeah, I mean not the hollow bell, the earth-filled bell. I'm confusing myself. Uh, and this analogy, work with me here. So our bell analogy, the ringing, it's much more subtle than the energy of the bell itself. The ringing and the vibrating, the hum of the atmosphere is much more subtle than the material itself ringing. And so that's what I'm trying to get across. Hopefully, maybe if you watch the video again, it'll make more sense. Please, if I don't know if what I'm saying makes sense, so please leave comments for me. I will answer comments. I will clarify this the best I can. I love the one-on-one interaction with you to know that you have it. And I've said this before, I'm not doing this for myself. I know enough. I ask them, help me with this. And I just want to offer this, that when I talk to my guides before I do this, please help me to present the information to the people that they need to know. It's not just about giving you the report of what this is, 5D, and we're moving into ascension, blah, blah. But, there's more to this than just, reading off of the chart, reading off of the graph, reading the spectrogram. It's not the Schumann, because there's a lot more information that comes with it, specifically the dependencies and what those are doing, the actual numbers are doing. All right, so the actual tone itself is the Schumann resonances. The vibrating bell, all right, we can think of it this way. One way to think of this, the vibrating bell itself might be the telluric currents, okay? They are, they're that much more solid, yet the harmonic is produced within the cavity of the bell itself. So even if you look at the telluric currents, like our bell, our hypothetical bell, and let's even call our in half of our bell hypothetically jello. All right, so we have the solid brass of the bell, and the other half is jello, and we're making a weird ringing in there with the sound of it, okay? And these are, the ringing of the bell, and the analogy of an actual bell is audio acoustic waves. These are pressure waves. That's not the same thing as electromagnetic waves. I've talked that before. Radio waves are electromagnetic. They're different than sound waves, but we have to use an analogy that you're more familiar with, that at least you could potentially see. You can see a bell, you get a close-up, you can see a bell ringing. So the best analogy I have that I can show you of the ringing is this bell. Professor Schumann used it, and so I'm exploring this analogy of a ringing bell. All right, so the vibrating bell pushes an air column, and it produces sound. Schumann resonances are not sound, which are pressure waves, which are mechanical function. Schumann resonances are radio waves that can move through a vacuum. Electronically, the process is similar in creating a harmonic. A vibrating body radiates out into the immediate environment, creating standing waves. Standing waves are fundamental waves that collide into each other, creating resonances, which are oscillations, which are closer to humming. Standing waves oscillate in place. Best way to look at this is that the waves or frequencies are not properly rolling or running, but they're running in place. Okay? Due to a common misperception of what energies and frequencies we are specifically talking about, there's such a huge misalignment of the basics of Schumann-side atmospheric electromagnetics. There has been an active program to confound the actual science behind the research. All right, so I'm not going to go into more of that because it's not necessarily here. I think I may do a video on that because it's a great post, and I really, this was actually a fairly long, I said a bunch there, it's and it's on my website, right? So you can go to my blog, it's there. But I think it'll, I don't know, I don't really read many of those, the announcements is for the group, but this is the website for the group, and I really think that what I wrote there is actually relevant to the website here, right? It matches up. It's because it talks about my philosophy and my mission statement, my philosophy, and it's taken me a while to kind of figure out how to put that. But I've been working on it, how to get that like a mission statement kind of thing. And so I want to post that out to the public in a video. The Facebook group is private, all right, by the way. So this is kind of the public video part of that. I don't know. I wanted to work them together, and it is what it is. All right, so anyway, all right, so I'm at 30 minutes. This was going to be a quick update. I'll probably post this as a premiere, I think, or maybe part of a live stream. Right? Maybe I haven't done that in a while. Well, I think I'll do a live stream. I got to go to the store before it closes, I think, and I get something to drink. And so then after that, I think maybe I'll do a live stream. I don't know. I haven't figured it out. Premiere live stream. I don't know. Who knows? But anyway, so I will talk with you all in a little bit, it looks like, and have a wonderful rest of your day if I don't, and you're just catching this on YouTube, whatever. So anyway, all right. Thank you all. Namaste.